So now that you got to know how ethanol is metabolized, but do you have any idea that what are the consequences of ethanol to other metabolic pathways? Well, some of the consequences are that it causes dysregulation in glycolysis, and some of those dysregulations can lead to lactic acidosis. Not only this, but it can alter Krebs cycle, it can suppress gluconeogenesis, and it can actually suppress the fatty acid oxidation. So it can cause multitude of problems in other metabolic pathways. While in glycolysis pathway, there is reaction involving glyceraldehyde 3-phosphate, which converts into 1,3-biphosphoglyceride. This reaction involves the enzyme glyceraldehyde 3-phosphate dehydrogenase, or GAPDH. This is a reversible reaction, and it requires NAD+, which get reduced to NADH. However, in case we have too high or excess amount of NADH, this can cause this reaction to go in opposite direction, leading to increase in glyceraldehyde 3-phosphate. So this can actually affect the glycolysis pathway at this step, and this ultimately reduces glycolysis. So what about lactic acidosis? Well, that thing acidosis occurs because pyruvate or pyruvic acid can be metabolized into lactate or lactic acid via enzyme lactate dehydrogenase. And this enzyme again converts NADH to NAD+. This is a reversible reaction because we have increased level of NADH, and this can push this reaction to side of lactate or lactic acid, leading to increase in lactic acid and leading to lactic acidosis. The TCA cycle or Krebs cycle is affected at the level of malate or malic acid. In normal TCA cycle functioning, malate is actually metabolized into oxaloacetate in the presence of malate dehydrogenase enzyme, and this is reversible reaction. In doing so, it reduces NAD+ to NADH. Now, during ethanol metabolism, the acetaldehyde is processed by enzyme aldehyde dehydrogenase, which occurs in mitochondria, and this led to an increase in NADH in mitochondria. So what happened is the increase in NADH in mitochondria. We will shift this reaction backward from oxaloacetate to malate, leading to increased malate, and this will suppress TTA, or Krebs cycle function. Now, effects on gluconeogenesis are a bit more complex, and it requires more explanation. I tried to explain gluconeogenesis in a simpler way. So what happened is, in order to utilize pyruvate for gluconeogenesis, pyruvate has to be processed through several steps, and it does that by getting processed to oxaloacetate and then malate in mitochondria. The malate then gets transported out into cytosol, processed back into oxaloacetate, and then oxaloacetate process into PEP, or phosphoenol pyruvate, which then can undergo several more steps, and then finally can be processed into glucose. Now again, during excessive ethanol metabolism, we can get high levels of NADH. The high levels of NADH again alter this process. High levels of NADH in mitochondria from aldehyde dehydrogenase reaction led to an increase in malate in mitochondria. But when we come out of the mitochondria, so if you pump malate back into cytosol through the malate aspartate shuffle, then there is also increase in NADH in cytosol as well, from alcohol dehydrogenase reaction, which take place in cytosol. So the increase in NADH in cytosol, which actually caused this reaction to push backward. So we are unable to adequately process malate into oxaloacetate to be used for gluconeogenesis. So this process that occurring in cytosol, oxaloacetate actually decrease as phosphoenol pyruvate, So all these actually reduces gluconeogenesis, and this led to hypoglycemia. So the reduction in gluconeogenesis function in liver leads to systemic hypoglycemia. And finally, ethanol metabolism has effects on fatty acid oxidation and synthesis. And it does so because of increased level of acetyl coenzyme A, which we have talked about before. So again, ethanol metabolism leads to increased level of acetyl coenzyme A, and this pushes reaction of acetyl coenzyme A in the presence of acetyl coenzyme A carboxylase to produce more malonyl-CoA. So increased acetyl coenzyme A and malonyl coenzyme A will lead to increase in fatty acid synthesis. Now on the flip side, increase in malonyl coenzyme A will lead to inhibition of fatty acid catabolism. So fatty acid metabolism actually decreases. Now this all leads to triglyceride accumulation, leading to fatty liver disease or hepatic steatosis. Long-term treatment with many drugs, for example barbiturates, causes proliferation of smooth endoplasmic reticulum and increases the activity of cytochrome P400 and 50 isoenzyme involved in metabolism and clearance of that drug from the body. Similarly, chronic ingestion of excessive quantities of ethanol causes increased proliferation of smooth endoplasmic reticulum and induction of these enzymes. This means that a person consume alcohol more frequently will metabolize and inactivate these drugs very rapidly and may need higher doses for treatment. Anyways, guys, that was about ethanol metabolism. I hope you found this video very informative. Thank you so much for watching. I will see you in my next video. Till then, bye.